Today we'll talk about ISA. All right. Actually, first thing first, let me also open up the chat on my Windows. I can see when people like asking something or saying something, because I'd rather see that as well for folks online. It's kind of hard to look at the screen and try to understand what's typed there. I'm too old to see the text. All right. Today we'll do a quick recap first on what do you guys know about ISA so far. So what do you guys know about ISA so far? Name one ISA. Give me one name. x86. Great stuff. Basically, these are the language for the hardware, right? The way I would classify this, and this is what I did so far in the system skill lecture as well, which is this is how we can talk to the computer. We just generalize these are the things the computer can do. These are the basic commands that if I say this command, my computer will give me some results. And I just have to then list the things that I would like to command the computer to do in order to program, right? So it means that we can represent human language, human instruction into the binary format, right? The binary format will encode basically your command and the data involved with your command. And this becomes the interface between your assembly code and your computer. And in the system skill class, right, we kind of develop the sense of like ISA as just the language, right, assembly. And you use it to well, you can use it to program. Computer use it to run. Program that you program in Python and C, use it to actually give the command to the computer. Then when you buy the processor, you're actually buying the hardware. So when you talk about microprocessor, it consists of two components. The first component is the ISA. It's like when you buy a computer, you get a language tagged to it. It knows that this processor speaks this language. That's the ISA. It's the command you can give to the chip, and the chip will do whatever you command to do. And just that command, not more. Nothing, things that are not defined in the ISA, the chip will like, I don't understand. Things that are defined in the ISA, you better have that implementation in the hardware to support that command. The hardware itself is the microarchitecture. Microarchitecture are the hardware. It's the art of putting the wire and transistor together so that you can run the command as fast as possible. For example, when you buy a new Intel or AMD chip, right? Let's say you buy the chip from 5 years ago. What would be the difference between the chip 5 years ago and today? What would be the major difference? Performance, right? Does the assembly language, does the ISA really change? Not really, right? It might have extension to support new features, new command, but in most cases, it stays the same. What is different is the hardware, the implementation. So that's the microarchitecture. And actually, that's like the majority of, I would say the majority of the architecture work that people who do ComArch and people who do system and people who do circuit are working on nowadays. Basically, given the same specification, how can we even build a better hardware? So that's the microarchitecture. When you buy a chip, when you buy a microprocessor, you get both of them. All right. So again, the key idea is to represent human language with the binary number, right? And sorry about the repeat slide, my bad. What does ISA consist of? Obviously, what you've seen so far, assembly code means that you have to have definition of these are the instructions that you can run, right? Add, subtract, multiply, right? Remember the move instruction from sysctl, the LEAQ, right? Those are the instructions. Inside the instruction, you have the opcode, you have the addressing mode. Remember the parentheses. The parentheses that confused you guys in the beginning. They say, what is this RB, RI, and the S? And you multiply everything. You have this G that add on top of it, right? Then the instruction type and the format, right? Then you also need to figure out, okay, if I want to design an ISA, how many registers should I give it to the programmer? right? If I want to design something for a really, really small embedded processor that goes into, I don't know, the thing that controls the air conditioner, right? Do I need a lot of register? Not really. I would rather save the hardware. Why? Because I can dump the price of the AC. I mean, I don't need a powerful chip, right? I don't need an Intel CPU in that thing. Why do I even bother paying for that, right? So again, but still, there are some ISA that say, hey, maybe we want more register because it gives the programmers some flexibility in program, right? How do you go access the memory? How do you manage things like the address space? Kernel versus user, how do you define them? Where are they going to be belong to? How do you manage things like the page table and things like that? Addressability, can I go and access each byte, each bit, each instead of each byte, each 4 bytes, each 8 bytes? Alignment, can I misalign things when I have a pointer access? If I can only access 4 bytes at a time, can I somehow align to like the middle of the bytes, right? Virtual memory management, and how do you the topic that you love so far, system call and interrupts and exception handling. By this point, you probably love it. It's like a love-hate relationship. Powerful technique. No love at all. Okay, good. That's when you can tell, like, hey, these are something I. So this is what I will always joke whenever students ask me, like, okay, what should I work on? What area should I dive into? I would always say there's no right answer. There's always a bunch of good options, and you kill out the option that you hate. My strategy exactly, right? I mean, back in the day, I'm like, hey, I'm dumb. I'm too dumb to do algorithm. Like when I take advanced algorithms, like I don't understand this thing. It's too complex, right? So I'm like, okay, I'll just know enough that I can be a good computer scientist, hopefully, and then go into system because it required a lot more of I keep coding. It's like putting the horn on my head and just keep plowing through. And at some point, it will work, right? Just follow the instruction, follow the guideline, follow the documentation, and more. It could work, and it will work eventually. Access control, who can access what, right? Priority privilege, how are they going to perform scaling based on these priority? This gives the OS. Basically, these are the tools for the OS. When you have this defined in the ISA, programmer, most of the time, you don't care about this. The OS designer now cares about this thing because it dictates how they would build the OS. How would they run the computer, right? How to handle I/O, how to handle threats, what has to be done. You have when you want to do context switching from one set to another, what do you have to do? Power and thermal management. If you want to look into mobile computing, for example, this can be important, right? How can I save power? And then there's also trade-off as well. And today we'll focus on that. We'll focus on the trade-off, right? For example, how complex should my instruction be? You have actually like a more deeper dive into this soon, right? But the next issue is like, how should I specify the instruction? This is like when you want to invent a new language, right? What should go into your grammar? What should go into the subject? What are the possible subject options? Assembly code will look differently for each ISA. You want to support fancy things like multi-threading is not fancy anymore. Back in the day, it was fancy. All right. Do you want to support low power operation? Do you want to support the case where you don't have a lot of memory resources and you want to be as efficient as possible? Do you want to support fancy things in architecture like what we call very large instruction word or VLIW? VLIW means that let's say I have one adder, one multiplier. Can I pack the instructions so that every single instruction do one add, one multiply because that can give me more throughput. I can do 2 things per instruction. We are not going to go into the detail of VLW in this class, but these are features like a SIMD. Anyone here heard about this word SIMD before? Single instruction, multiple data. What what is the type of processor that relies on SIMD? Like without SIMD, this thing will not sell at all. GPU. GPU performance come from a bunch of things. One of that is SIMD, the other one is fine-grained multi-threading. Fine-grained multi-threading basically means that I have a bunch of hardware threads. So instead of context switch, I can maintain multiple program counter. And then every single cycle, I switch to another thread. By default, I don't do the same thread again. That means that, let's say I have to have memory access is spending 100 cycles to go to the memory. I have the other 99 threads to switch in. By the time I have to run the next instruction, my data is available. I don't care. So that's how GPU works. So the type of ISA also includes things like the complex ISA versus the reduced ISA. We're gonna have toward the end of this lecture. Toward the end of this lecture, we'll have more like a. Now let's look at what is CISC, what is RISC, and what are the trade-offs. Now, again, the instruction. Now let's expand to the first thing inside the ISA, the instruction. You don't have a functioning computer if you cannot give them the command. All right, this is the definition of given a computer. These are the commands you can do. Think about it this way. If you want to design a language like C, right? What can C do? How can I do an add? How do I define? I'm adding right now. So quick question. Can I define a programming language that doesn't have the addition support? I don't have the add, but it's still like a Turing complete machine that runs. Yes. It would just rely on a bunch of and or, right? It would be annoying to program for sure, but it would work, right? But then the typical question from everyone else, like who will buy this programming language? Who's gonna use it, right? It's gonna be pretty useless. So the goal is the same here. I want to build a chip. What should be the most basic elements of command that I need to support? What, now that you cover the basic stuff, right? What should be the more complex instruction that I should support? So the main components of the instruction is opcode and operand. You see this already in Cisco, so I'm going to go quickly. Now, for the purpose of this class, I will simplify the ISA. We are not going to work with x86. We'll work with my own simple ISA that have the command name, which by default should be pretty self-explanatory. Add means what? I add two numbers. The register go from R0 to R1, R2. It's no EAX, EBX, just start from 0 to N. This means I want to add R1 and R2 together, write the result to R0. And whenever I define the instruction, I will tell you what does the instruction do so you know the detail. All right. Now, element of ISA, we talk about control flow and data flow computer already, von Neumann and data flow from last week. Now, do you want to support the sequencing model? When you run the application, do you go control flow or data flow? Or are you doing control flow but fake data flow inside the microarchitecture like the Intel and AMD chip? Processing style include things like number of operands. You see something weird with x86, right? You have source, you have destination, but it's only one source. Where's the second source? Remember, let's say I want to add something together, right? Add, and then there's like EAX, EBX, and that's it. Now that's your add instruction in x86. Only have two operands. How many inputs does the add require? Two, right? So over here, x86, we can call it as two address ISA. You have op, source, destination. Op means operation. And then the second source actually comes from destination. You do is basically what you do is A equals A plus B. You don't have the third operand, right? There are trade-offs to that. For example, now you can pack more things. Like instruction is going to be smaller. right? Because you only have to specify 2 things rather than 3 things. Now, back in the day, we have things like a stack machine where you don't have a lot of support for the register. So you have a stack in the memory. You have the CPU that can do operation. Whatever you have to do, push, and then pop to do operation, which then allow you to push back. That's it. That's your register and your operand. You don't have the register. You only have the stack. That's it. All right. So that's a really, really ancient machine where you don't have a lot of resources to build the hardware. You can have a zero address machine. It doesn't even have the operand. Everything is on the stack, and you pop to do the operation, and you got the result. Either push it back to the stack or do something else. All right. Then it evolved into accumulator machine. Now I can load from the memory. Imagine you have the memory now. You can load something, which means I can read from it. I can write to it. And then I have the accumulator, just a single register that can perform operation. Load, do something, accumulate, do store it back. Super simple. Then you have things like x86, and then it also, like nowadays, many modern devices like RISC-V or ARM processor, I believe, the 3 address machine, which you have 2 source, one destination. Makes sense, right? Because your operation either have 1 input or 2 inputs, or 3 address. Makes sense. That's it. That's all you need. So the trade-off, again, space, how compact can one instruction be? Things like code size, and also number of executed operations. So you have the operand. Now you have the operand specifier, which include things like, remember the parentheses around register in x86. That whenever I said, if you see parentheses around something in x86, that's an address. That's the operand specifier, right? Or what's the dollar sign in x86? What's dollar sign? Value. When you have the x86 assembly, you have dollar sign next to something, that's a value. Treat that as a constant value or immediate, right? So parentheses means address, dollar sign means constant, nothing means that is your register, right? So it would tell you how do you use the operand. You also think about the data type, like floating point, character, integer, binary, decimal. You also can support complex structure like x86 and wax, which let's call. It can be like, I want to build the operand that actually point to the beginning of my array. And then I do something on an array. If I want to, I can design an ISA that work with array, right? Now, complex instruction can include things like, how many people know what's a convolution? Okay, so if you do machine learning, for example, or signal processing, image processing, you're gonna have to do this a lot. Convolution means it's kind of like when you have 2 signals coming in and it's an operator on 2 input function that perform like series of like window multiply, and then you accumulate them and have multiple data points. So 2 inputs are function, you produce function as an output. And it's used for image processing, signal processing, machine learning. We can do an instruction for that if you want to, which means I need to have a hardware to support it inside the hardware, right? But it would be really nice if my chip do things like image processing, okay? Means that I do a lot of convolution. I can have a instruction that would initialize an entire array, right? In one single assembly line, one line in assembly, everything is initialized, right? I can pre-build it in a complex ISA or CISC ISA. We'll go into more detail what CISC versus RISC. You might have heard it so by now, but we'll go into more detail. You can also have simple instruction like add, XOR. Like these are things you know your friends so far. And always complex operation can be built from simple instruction, which means that you have adder, multiplier, and the add and multiply operation. You can do whatever you want in the program, in the software, in assembly to have a functioning program that will be equivalent of the same complex ISA instruction. Now, what is the benefit of complex instruction? Well, you can have small code size, right? For example, if you have to initialize your array to 0 and you have the instruction just for that, you can use one instruction, everything becomes 0. In Intel, for example, have this, my advisor love to use this example. It's called instruction wrap move up. It's repeat move. So instead of one single move instruction, now you can do move until some condition becomes true. That's a loop in one line, right? So denser encoding means what? Your program is going to be smaller because instead of having to write a loop, which by multiple instructions, one instruction, one line, you're done, right? I would like to use the word back in the day, but it's actually the fact. Back in the day when I was like a high school and middle school student, right? Back then, DRAM is not even 1 gigabyte in size. So your program, the size of your program matter. Because if it's too big, it might not fit into certain computer, right? So you want to care about the instruction size. Even today, if you have embedded processor, your instruction size also matters. The processor that go into like air conditioner, your refrigerator, those things has really tiny chip in them, right? But it's tiny, you can store a lot of things. So you might want to use these kind of stuff, right? There's also another thought process which would say, hey, we just have simple instructions. That's it. The rest, I'll just rely on the programmer. Hopefully they can do that job, write the loop properly in assembly, or the compiler to compile your loop into assembly, right? To simplify the hardware, which means what? Also, it's likely that I can clock faster because my hardware is simpler. Also allow more, yes. Simplify hardware means, okay, think about it this way. Let's say my ISA consists of 1,000 instructions. The first 100 are the basic thing, add, subtract, multiply. Then the other 900 are like add into an array, dealing with repeat move as, for example, right? It means that I need to build the hardware for each instruction. There has to be a transistor dedicated for each instruction. Then another thought logic comes in to say, hey, I mean, I can write a totally functional computer with the first 100 instructions. Now I only need fewer transistors for sure, right? I don't have to support those things. So for sure, I can use fewer transistors to build just the first 100 instructions. Then, given the same chip area, right? Let's say your CPU come in that size, right? I can use a transistor for things like the cache, right? Or logic to make your CPU faster, right? So it's a different thought process. Do I use transistor for fancy instruction and optimize these instructions so that they're really fast? But the overall CPU can be clocked at lower speed. Or I have a simple CPU that has simple list of instructions. Then I use a transistor to do fancy implementation that would speed up your CPU. Now we have this already about semantic gap, right? I can have a large semantic gap where your ISA just do raise this voltage, lower this voltage, which would be annoying. This is kind of like there are a few proposals these days about quantum ISA. How do you program quantum computer? And they're about at that level right now. Or you have a small semantic gap where, as I said, looks like a high-level language like C, right? And you can imagine to do that, you have to have a lot of hardware support for each instruction. And then the translation means I change the semantic gap. So you've seen those slides already from Cisco, so I'm going to go a little bit quickly. Trade-off of different data types. These are new. What's the benefit of high-level data type like a linked list or an array? Abstraction, right? And to be honest, we use it a lot. We use lists a lot. We use array a lot, right? Maybe we want to support array in the ISA. The notion of this pointer points to the beginning of your array. This pointer stores the size. If we have that, what are the fancy things you can do, right? Let's say they have a special pointer that points to the beginning, another register that say this is the size. So now you know the array, right? Downside, well, you got to implement the hardware for that. Let's say you want to do array traversal, right? Need to have the hardware to perform array traversal, which is not simple, right? Again, this affects semantic gap. It means that your assembly code can just maybe initialize an array in one line, right? Then the hardware has to be built for that. Memory organization. Okay. How many unique locations you want to support in the memory? For example, you might want to define, well, obviously you want to define a unique location for your kernel space versus your user space. How do you support multiple address space that way? Do you want more? Do you want special region, for example, for your IO? Say, hey, everything goes there is like IO, so that you can stream things in and out more efficiently without relying on the CPU all the time. Should you make, yeah, I say so that you can only access each byte or each bit or each 32 or 64 bits. And this can be make basically everything is programmable. If you allow, for example, only 32-bit addressable, means that you can only access 8-byte chunks, not any individual bytes. You can always write an assembly to extract just 1 byte of that 8-byte, right? So everything is programmable. It's just a design choice by now. Everything is about the design choice. How do you want to support virtual memory? There are actually multiple new virtual memory proposal, right? Do you want to support those fancy things in the ISA? Do you want to do that in the system? Do you want to support big endian versus little endian? These are specified in the ISA, or both of them. If you want to support both formats, how do you specify what format are you working on right now? How many registers do you want in the ISA? How big is your register, right? Good question. What's the difference between RAX and EAX? Anyone remember? I heard some laugh. Both of them are return value. One is bigger, one is smaller. EAX is 4 bytes, RAX is 8 bytes. They point to the same guy. Just took the last 4 bytes of the 8 bytes. RAX is 8 bytes, EAX is 4 bytes. Why does it work? I mean, for example, you use long int. Which one are you use? RAX, because it's 8 bytes. If you have int, maybe EAX, because it's 4 bytes, right? So register benefit is these are really, really fast, and it allows you to bring the data in front of memory, take advantage of data locality. Yes. What do you need 16 bytes? That's a great question. How many data types support 16 bytes? No, I'm not trolling you. I'm just asking another question back to you. Because that's a certain answer to that. Yes, you can support 16 bytes. It's also the element where I say you can. The problem is then you also need to make sure everything works with 16 bytes as well, but with the 64-bit machine, your address is going to basically be 8 bytes. So everything's kind of built around this 8-byte notion. Everything, the data part means that your hardware that run your CPU actually designed around 8-byte concept. Like you move things in the 8-byte granularity. So yes, you can do 16-byte support. The way you would do it in hardware, we'll do the trick called microcoding. Microcoding means that I have think of it as a simple program inside the hardware that would do maybe 16-byte addition by going through multiple steps using the same hardware. But this is like a mini instruction that say, if you want to do 16-byte addition, you do this followed by this, followed by this, followed by this, followed by this. With one instruction, you're gonna basically go into micro instruction, internally defined in the hardware, not exposed to the programmer. So you can definitely do that. So yeah, you can make register. Also, you can make register 16 bytes as well. But think about the size basically doubling, right? Because 8 bytes is a half size of the 16. Right? So you want to support 16 bytes, your register file is going to be twice bigger. If you need a twice bigger register file, now your decision is this. Let's say you have 8 register of 16 bytes. Another option is I have 16 register of 8 bytes, right? Because it uses the same capacity, right? It's 8 multiplied by 16. You get doubling the number of register to use, right? So it's again, now it becomes a trade-off. Which one benefits you more? The answer most of the time is most of your data size will not use 16 bytes. So that's why I asked in the beginning, like how often do you actually need to use 16-byte things? Like except maybe floating point. Maybe float like if you do 64-bit floating point, I guess you can extend to 128 bits if you need really accurate data. Yeah. So the use case diminish basically, right? So one thing about hardware design is most of the time you design for the common case, except for when you design special hardware. So you either go to super common cases and optimize for that, or the super unique cases and optimize for that. There's not a lot of middle ground. So, yeah. Now, register also evolve over time. Used to be just I can add things, accumulator. I can add 2 things. That's it. That's what my register can do. I cannot even use it to store things. I can just store something temporarily and accumulate. Then I can handle address. So I have accumulator and a separate register that say this register store an address. So one set of register that store accumulator. The other set of register that store location. And you use the address register to point to the memory. It's like, that's the guy I want, that's the guy I want. Put it into the accumulator, add the 2 together. That's it. That's all you can do. Why? I mean, imagine the 1950, 1960, right? You don't have a lot of fancy things. Now it kind of evolved to general purpose register. Your temp variable that you can use to program. Do whatever you want with it. It can range from a few registers to Intel Itanium, which I think deprecated by now. It's like it died. Basically, Intel IA64 has 128 register, which is a lot, right? What are the other elements? You have addressing mode. How do you obtain the operand? Remember the parentheses. Parentheses. You can have absolute. Go to that address. 10. You can have register indirect. Use the register as a pointer to the memory location, or you can use display base, which is what x86 use. You have the base. You have some range from it that you can multiply and add to the base. Most modern ISA support all the 3 types. Most modern ISA support all the 3 types. And each ISA has a definition of how you want to address and how the addressing mode is specified. There are benefits of more addressing mode because you can reduce the number of instructions, reduce the code size, right? If you assembly again. Remember your old friend? This is something I'm sure that many of you forgot. What's that? Anyone remember that? So I can do something like this. Something like this. Oh, I want to write something. What is the address I'm trying to access? Anyone remember? And it's okay. I know how it goes. Every time, like whenever I'm done with the exam, I forgot whatever I learned. That's okay, right? This basically means I have RAX plus RBX multiplied by 4, right? Plus 20. And these are useful when you want to do like array access, for example. Right? Let's say you have A of I and A is an integer array. You want to make sure your pointer starts from the base. Then you go 4 at a time. Base plus 4, base plus 8, base plus 12. So the scale 4 usually means that the size of your data is that big. Then RBX is the index from the base. And RAX, in this case, you use the base where the pointer starts at. Right? The downside of this, more work for a compiler, but it's okay because I'm the comart guy. I don't do compiler. I just let my friends did that. All right, joking, but yeah, basically means the compiler have to do more things to optimize for the fancy features available in the ISA, right? I would need a more complex compiler to handle the addressing what should go into RB, what should go into RI, and what should go into S, and do I put D at all? Also, more work for a micro architect. Because it basically means I need to build the hardware to support that operation. The operation is 2 addition, and 1 multiply, right? Handling this address, multiply, because it's multiplied by 1, 2, 4, and 8, I can replace that with a shift. So it's shift left by n bits plus 2 more number. How do you interface with I/O? Do you want to do memory map I/O? Basically means that these part of your memory belong to, for example, your monitor. Whatever the value you put there, the monitor can come in and read from it and show something on your screen. And it's only belong to the process that draws something to the monitor. It has its own address space. Right? Load and store the data allow the processor to interact with these I/O. You want special I/O instruction that handling I/O device. How to handle user versus supervisor. How to have, let's say OS want to do scheduling, right? How would you set who get to run next? In x86, how did you do that? Anyone remember? How do you do context switching in software? In context. All right, what's context? Okay. All right. So basically, the CPU has its own state. These are the register state that my program is in. These are the program counter, the line I'm running right now. And let's say the OS, which is the guard comes in and is like, hey, stop, I want to run something else. What do you have to do? Hack everything up, move to the memory. All right. And then OS will pick another thread and say, okay, that PC goes here. Your register you save already goes into the register file, resume execution. That's how x86 handle things. You save the register state, you save the PC, and you switch context. How do you handle exception and interrupts? Procedure to follow when something goes wrong. These are typically defined in the ISA. So what you did so far is for x86. For a different ISA, go read the manual because you have to set a different thing. So how you have to set certain register with a different value. Procedure to follow when external device requests something, like I type something on a keyboard or I move my mouse, right? And like look at imagine a mouse, right? How many input and output requests are coming from your mouse? When you move it, right? It's actually tracked. The laser, like let's say you use a laser mouse, right? Every input that it registers goes to your computer and it has to handle that. Right? It's quite a lot. Vector versus non-vector interrupt. So it's more the module one, but it starts from here. ARM ISA, for example, have a different definition. ARM has like a table to say, if this happened, go to this pointer, and then you build a function that the pointer points to for the interrupt handler. How do you manage virtual memory and address protection? Now, there's a class of instruction this is I think the second time you said this. So you have compute instructions like add and multiply. You have data movement, load, and store. So we are not going to talk about the move instruction here, on the memory instruction here. I'll call it load and store. The only key difference is load is reading from the memory, store is writing to the memory. Control flow, branching, right? Change the sequence of instructions that are executed. Now, you have the load store versus memory to memory architecture. Load store architecture is what you've seen so far. I put something to the register before I can add. If I want to add two things, I would say I want to add EAX and EBX. Those have to be in the register first. So you load something to the register, you perform computation, and you store it back. That's the load store architecture. Memory to memory architecture means that I want to build the support to say I want to add address 10 and 20 together. That's it. I don't have to put that in the register. I want to add that memory location with that memory location. Many old CISC architecture support memory to memory, but back in the day, memory is actually expensive. Register is expensive, so you want to be able to support this. So again, the trade-off, right? Load store kind of simplify a lot of things. Everything you do, put in the register, and then you build the hardware, operate directly on the register. Memory to memory means that I have to have the dedicated hardware to deal with where do I go to the memory, then what do I do with it? There's also ISA with the fixed length instruction like ARM and ARM and RISC-V. ARM has a fixed length. It means that my always this typo. I need to fix my slide. It's like every semester. Easier to decode. Decode means that I have bit stream coming in. You need to figure out what that instruction is. This is going to be the majority of your project rate. You have bit stream coming in form of that's the memory that program counter is pointing at. What is that instruction? All right. Fixed length is easier because every instruction will have certain size. So let's say you're at instruction 2, and the address is at 0x10. Where is instruction 10? Okay, quick question. Where is instruction 3? If I say each instruction is 4 bytes, where's instruction 3? It's going to be 10 plus 4, right? 0x14. Instruction 4 is going to be at what? 0x18. Which means that you can always tell where each line is going to be in your memory. Because every single line is the same size. It's easier to say, hey, I want to now, let's say, how many people think that it's maybe beneficial to, instead of pulling in one instruction at a time, I'm going to pull maybe 4 instructions at a time. In case the first one is adding, the second one is multiplying, and I have one adder, one multiplier, I'll just do them both at the same time. So how many people think there's a benefit to pulling multiple instructions at the same time? right? Because it's going to be faster, right? There's more opportunity that you can do things in parallel. Fixed length is super easy to say pull 8 instructions because you know where the beginning of each instruction are. You also have the easy to decode multiple instructions at the same time because if I need to pull in instruction 1, 2, 3, and 4, I know where they are, I pull it in, I'm done. The problem is it can waste bits. I mean, sometimes your instruction doesn't need the entire 4 bits, 4 bytes, right? Sometimes your instruction might fit in just 1 byte, so you can waste the space. Also, it's harder to extend by extending that. Let's say I want to add fancy instruction to my ISA. At some point, you will run out of bits, literally, right? You only have, say, 32 bits. That's it, right? If you use all of them up, well, that's it. You can't do anything more. I mean, to be honest, with the 64-bit machine, you can now extend instruction to like 32 or 64 bits, which is a lot already. So the extension is usually not the problem now. And here's one example for RISC-V. RISC-V is this, again, I'll mention this project. It's like an open essay started in Berkeley, UC Berkeley, by a collection of really, really senior professors in architecture. And the project is say, hey, nowadays one of the problem with hardware startup is you always have to rely on either ARM or x86 because that's it. That's the ISA you have, right? And the issue with that is it means that I cannot have any startup that modify the ISA. It's gonna be hard for me to have it available, right? So one of the key goals is let's have a standard that say, if you want to use this ISA, no one has to pay me. It's all free, it's all open, you can use it for free. It's not like ARM, where you have to pay ARM to use the ISA, or x86, pay AMD to use their ISA, right? Now, hardware startup, let's say I want to build a special chip for X and Y, can use RISC-V, and make sure that it works with some basic OS, and then you can plug it into like maybe a computer or data center that use like, I mean, it's okay to plug into another computer, use ARM or x86, but it works as a standalone hardware that runs RISC-V. So the project used the ISA called RISC-V, and it is a fixed size format. It has 16-bit format and 32-bit format, and as you can see here, each row corresponds to the type of instruction, and you can always say, for example, the first 7 bits, bit 0 to bit 6, that will be your opcode. If you want to figure out if you are dividing, multiplying, adding, loading, or branching, extract bit 0 to 6, you can tell right away. Then, based on the opcode, then you extract different parts of those bits. Project tree is going to be similar to that. You look at certain bits and say, hey, this is what you do, then you extract the different set of bits for your operation. You can also have the variable length ISA. Give me one name that you know. Yes. x86. Remember example where I say, hey, this is a for program that say a equals 0, b equals 5, and return a plus b. Let me pull that example for you because we just covered that in Skill. Give me a second. It's this one. Oh. Remember this guy. All right, let me zoom it in. Remember this example? Look at how big each line is. The first line is 1 byte. The second line is 3 bytes. The second line move RST RBP, that's 3 bytes. Then move L with 08 RBP, that's 7 bytes. So let's imagine you need to build the CPU. and you want to bring in the first 4 instructions. How can you tell where is the second instruction, right? So to be honest, Intel does this, AMD does this, and they have a complicated logic to do it, all right? But it involves a little bit more steps because you need to first figure out, okay, for the first instruction, how many bytes it is before you can extract the second instruction, all right? So now you probably know the idea. You have variable length, right? The benefit is your code is going to be more compact. If you look at the timeline of x86, when was x86 invented? How long ago? More than 19, yeah. How many years is that? 30, more than 30 years ago, right? It was back in the day where memory is precious. Memory is precious. So compact encoding actually has a lot of benefit. Your program binary is going to be smaller, right? Also harder. Well, the downside is harder to decode, but you don't even know. Like, you don't even know, do I bring in 1 byte or 2 bytes or 3 bytes? If I bring in 3 bytes, do I have to do what? X, Y, and Z? It depends, right? Over here's one sample instruction, 3-byte VEX instruction that has 2 formats. There's a 3-byte format and 2-byte format. You saw that on the system skill assignment already with the push instruction, right? It has like different formats. For each format, it uses different number of bytes, right? So now there's a trade-off here. You can do uniform decode. For example, look at RISC-V. Remember how the opcode is always in the bit 6 to bit 0. It's easy. You always extract those bits. You know exactly what you have to do, right? So that's uniform decode. The position of each bit corresponds to certain things, and it's always that thing. So it simplifies the hardware design. It allows more parallelism as well because you can just extract the bits and you know exactly what you have to do. So you can do a lot of things in parallel. But again, it can waste number of bits used for your program. Non-uniform decode is more compact. Like look at Intel x86. So basically, this is RISC-V versus Intel x86. Oh, AMD x86. Sorry, my bad. It's like x86 64. Non-uniform decode also is easier to extend because if you want to add new instruction, yeah, you can use any number of bytes you want as long as it fits, right? And then the definition of fit is what? Infinite number of bits. But your decoding logic will be much more complicated. All right, example time. Actually, let's take a quick break before we go through example. I'm gonna illustrate because I talk a lot already about the benefit of simplicity, right? RISC-ISA seems good. Uniform decode seems good, but let's go through some example. Let's build a simple, really simple essay. Okay. Before we go there, let's take a 5 minutes break. We'll be back at 11:10. Yep, what's up? Let's say I want to design a simple CPU that can only do this. I want to add, I want to multiply, I want to store something to register, and I want to load a value from the register. So it basically means that I can add, multiply, load, store. And when I want to store, I can store 2 formats. I can store a constant to the memory, and I can store a register value to the memory. All right, and that's it. Those are the 5 things I can do. Add or multiplier take 2 inputs from the register and write the result into the 3rd register, right? And you have 4 registers in total. Let's assume that I'll call them R0, R1, R2, and R3 for the sake of simplicity. All right. And assume one instruction is 16 bits long. Basically, every single instruction is going to be 16 bits long. All right, half one. Given this assumption, right, the first question that I need to ask is, okay, how many different operations I have to support? 5, right? Add, multiply, load, store, and store constant to the memory. 5 things. If I want to support 5 different operations, how big do I have to use for the opcode? 3 bits, right? I can use 3 bits. I can say if my opcode is 0, 0, 0, that's an add. 0, 0, 1, that's a multiply. 0, 1, 0 is a load. 0, 1, 1 is a store. 1, 0, 0 is a store immediate, store constant to the memory. Whenever I use the word immediate in, I guess, in computer engineering, it means constant value. Now, the next thing is, well, at for register, how many bits do I need for the register ID? 2 bits, right? I can say if the register ID is 0, 0, that's R0, 0, 1 is R1, 1, 0 is R2, and 1, 1 is R3, right? For each instruction, how many registers are involved? So add and multiply is going to involve 3 things, right? Source 1, source 2, and destination. So 3 registers. Load and store, 1 for the data, 1 for the address. I want to store this data in this address. I want to load this address into this data. So 2 things. For store constant is 1, just the target. I want to store something at this address. Okay. Now let's do, yes. Add has 2 inputs and 1 output.
Okay, for each instruction.
Yeah.
Like for animal design, it's 2 input.
Yeah. That's x86 2 addressing mode. I'm assuming that we have 3 addressing mode where you have source 1, source 2, and destination. So it means I can be more flexible here. Yeah. But it is your, basically it depends on our definition. We can do that as well, for sure. So for add and multiply, let's do the bit pattern. I said already, it's like if the opcode, right, is 0, 0, 0, that's an add. 0, 0, 1, that's a multiply. All right, quick question. Where do you want this bit to be? It's your choice. At the top, at the bottom, pick something. Do you want the opcode to be at the bit 0 to 2, bit 15 to bit 13? All right, 0 to 2, okay. So, okay, here's your opcode, right? Bit 0 to bit 2, it's going to be either 0, 0, 0, or 0, 0, 1. Now, what are the other information that you need from it? The input and the output, right? Let's call it source 1, source 2, and destination. Okay. Where should you put it? Okay, let's make it easy. Let's put it next to this guy. Right? Let's put my register next to this guy. So, source 1, source 2, destination. This is bit 3 to bit 4, bit 5 to bit 6, bit 7 to bit 8. Are we done? What else? I mean, do you need anything else? That's it, right? That's it. The rest we can just say don't care. Whatever bit here, I don't care. If my opcode in the last 3 bits is 0, 0, 0, 0, 0, 1, I just need that 6 more bits. All right, 9, 10, 11, 12, 13, 14, 15. When I write in X, and when you see X in bit pattern, usually what we call this guy is don't care. It can be 1 or 0, we don't care. It can be some noise in the electric signal, we don't care. Right? So if in an add instruction, it's going to be basically don't care. Then you have the destination, source 2, source 1, and then 0, 0, 0. So let's say I want to add something like this. I want to do R2 plus R1 and write the result back into R1. what's source 1? Let's assume the left guy in the addition. Source 1 is R2, right? How do I represent R2? 1, 0, 1, 0, right? R1 is 0, 1, destination is 0, 1. So if you see this bit pattern, 0, 1, 0, 1, 1, 0, 0, 0, 0, you know that add R2 and R1 together, write the result back to R1. Now we can do the same for multiply. The last 3 bits will change to 0, 0, 1. That's it. That's all you have to do, right? Any question about this? Now we're designing our ISA, basically. These are what our ISA can do. These are the bit pattern that correspond to the ISA. And it's basically your choice. Right now you said, hey, let's put the source 1, source 2 next to the opcode, right? So we are done with 2 instructions. We have 3 more left. Now let's do the load store. We said load can be 0, 1, 0, right? So that's the opcode. Do you want to use the address register first or the value first? You basically load. What's the source of the load? An address, right? So here can be the source and the destination. So let's say, for example, you want to load whatever address R0 into register R1. Basically means that the source is 0, 0 because it's R0 and the destination is 0, 1 because that's the register R1. What's the rest? Don't care, right? For store, it's basically becomes 0, 1, 1 at the end for the opcode. And let's say you want to store the value at R2 at the location R1. It means I want to put R1 as an address. I want to store whatever R2 is holding at R1. So here it can be, again, source, destination, right? Source here be R2 and this R1. Same thing. Yes. Okay. Another trick that people can do as well, instead of we call this source or destination, we can say this is an address, this is the value. So now in this case, this is going to become 0, 1, this is going to become 1, 0, because the one that has to do with an address is R1. So this way, when you extract the opcode and see 0, 1, 0 or 0, 1, 1, you know whatever is having to do with the address is going to be in the next bits. And then whatever has to do with the value is the next set of bits. Your choice as well. Basically, where you place these bits are your choice. We are the designer, right? Now, the last instruction is I want to put some constant in the memory. For example, I can do store immediate. I want to store 0 at the memory that points to by R1. Basically, R1 is an address. I want to put the number 0 there at that address. All right. Opcode, we said it's going to be 1, 0, 0. Now it needs 2 information. The first information is a register ID, right? The address. So in this case, R1 is going to be 0, 1, right? Then how do you represent 0? 0, right? Here's the thing. How many bits do we have left? It's 16 bits long. We use 5 bits already. We have 11 more bits. This is going to be the immediate field. Whatever goes there is my constant, right? So this is the part where the instruction length matters because in this case, I can represent a number from 0 to 2 to the what? 10 minus 1, I think. 11 minus 1. I have 11, 2 to the 11 minus 1, my bad. Basically, now my address can go, my constant can go up to just 0 to 2 to the 11 minus 1. If I have a bigger instruction, I can go bigger with a bigger constant, right? Now, putting everything together, we have all the instruction there, right? Add, multiply, load, store, and handling constant to the memory. Can you program with this machine? Yeah, it's fine, right? Is it annoying to program? All right. So, quick thing we learned, we can build a computer or we can build an ISA. We can define what we want to support. Now we basically say, hey, we will follow this opcode and operand. You have the list of instructions. Then you would extend, okay, with this computer, how you would handling address space, how you would handling interrupt, how you would handling the case where you have to context switch and all those things, right? But here's the basic elements. Here's the basic elements. Now, the complexity of instruction is CISC versus RISC. CISC stands for complex instruction set computer. Back in the day, we used the word computer. These days, complex ISA. Complex ISA come from the school of thought that say, I want to build an ISA that can support a lot of instructions, because why not? I want to make sure the hardware can do vector add, vector multiply, because why not, right? And here's the trade-off. The instruction that a complex can take multiple clock cycles, and that's fine. I just make sure they take multiple clock cycles, because if I want to do a vector add, like add a bunch of things in my array, that would take a while, because it's actually a bunch of add operation, and it's okay. Each instruction can do a lot. I can even support memory to memory instruction. I want to add two things, but both stores are not registered. Both stores are in the memory. Or you can do something like an Intel processor or AMD x86 processor where it's registered to memory. One of the operand can be memory. The other one of the operand is like EAX, right? This you give you small code size. What we call is, this is a CISC ISA, complex instruction set computer ISA. The word computer and ISA basically kind of refer, like there's a historical reason why we call it ISC. We change to ISA now. All right. Example of this is x86 and the wax machine. Wax is an old machine that has even more instructions supported. You can probably imagine instruction being supported for whatever operation you want to do. It means that my transistor is going to be built dedicated to run those instructions. Okay, it makes sense for certain operation. It makes sense for certain use cases. It also doesn't make sense for many other use cases. For example, how often does your program do things like, I don't know, matrix multiply? Depends. Yeah, depends on what program are being run, right? Why don't you just say, hey, if you want to use matrix multiply, implement that in software, write assembly code to do matrix multiply, because I want to use transistor for my cache, right? So that's another chain of thought for the RISC design. RISC design say, hey, I want to design my ISA to be, it's okay to be more restrictive. I can support maybe the first 200 instructions that are crucial. Add, subtract, multiply, add immediate, multiply immediate, division, and or XOR, shift, and all these basic operations. Then I'll trust the compiler folks to compile your program into something efficient in assembly, right? Then everything I have to do, all the operation has to be in the register. So it's called load store architecture, which means that if I want to do any operation, it cannot go directly to the memory. It has to be brought into the register first before you do an operation. Typically, because you only support a few instructions compared to a CISC architecture, your clock speed is a lot faster because it's simpler. Your design is simpler. So you can clock faster. Most of the time, you can have a deep pipeline, simpler design, fast clock. Now, here's the deal. I use, let's say in the CISC architecture, I use 100 units of transistor for my hardware, for my ISA. In this design, I might only need 50 units. The other 50 units, I'll use it for more cache, more complex logic to maybe I can fetch 5 instructions at the same time rather than 3. I can use transistor for that purposes as well, right? So that's the thought process. Yes, question? Yeah.
But that is really anything support.
x86 support where? Oh, x86 support register to memory. So one of the operand can be memory.
So ARM does not.
Yeah, it does not.
So like the V8X max for memory, but x86 is like register.
Yeah, WAC is like designed for the time in life where memory is expensive, basically. There was a time when so think of it this way, right? Here's the trade-off of CISC, right? It means that for whatever transistor I gain, I can get more cache. And for whatever transistor I gain, I can get more logic for my memory. And this benefit will go up and up and up the cheaper memory becomes. The cheaper SRAM becomes. I can then use even more, right? I can even use transistor for even bigger cache. This style is called the RISC ISA. Some of the prime examples of this is like John Cox, IBM 801, Dave Patterson, RISC-1, which now evolved to RISC-5, with so many contributors from the academia. As far as I know, it's also many shipped in China based on RISC-5, and also many shipped in Europe and USA revolving around this design. Also John Hennessy MIPS, which is what you're gonna implement. ARM processor, but ARM is a little bit special here because ARM has element that looks like a CISC in them. Here's the thing. There's no need to stick to one of these designs, right? You can have a design that's like, here's the core idea would be RISC architecture, but then you do the extension that could do complex things. If you want to, if you need that support. Yes.
Is that why right now
Oh, yes and no. ARM also has there are many processor design optimized for ARM already. So it's kind of like if you want to launch a product right now, it's much easier to get it done. For the RISC-V design, I start to see new chips that are still in the research phase that say, hey, we are trying to compete with the performance of ARM and x86. It's not there yet because still, well, more people need to work on it, basically. I mean, imagine how many people work on, like, for example, work at the company that built ARM chip, like Apple, NVIDIA, Qualcomm, and Samsung, right? Compared to startups that work with RISC-V.
something that RISC-V is like
Potentially yes and no, depending on the microarchitecture. Now, at this point, the rest of the detail goes to the what do you want to put in the hardware? What's your design decision? What's your optimization? One good example of a blazingly fast ARM chip, M2. That's really fast, right? Also, one good example of really fast x86, Intel and AMD chips that are used in data center, right? Then it's just a matter of what you want to use this transistor for to make your processor faster. And that matters so much for performance beyond what you learn right now, which is like, okay, these are the instructions you have to support. When you look at RISC-V or ARM, it's just a list of instructions that you can support. There's so many more detail on how you would implement these things. And then what do you want to use with the spare parts that you have left, right? Quick bit, I think the first 3 guys already got Turing Award. First three guys.
Oh.
Yeah. John Hennessy and David Patterson. If you are anywhere in the world and you buy ComArch textbook, I would give my bet on it's gonna be the book by these two guys. That's like a ComArch textbook that we would use one of like by default. There's a few common ComArch textbook. One of the most common is John Hennessy and Patterson. They co-author one textbook used in many US colleges. The other one is from Yale Pat, is my grant advisor, like my advisor from UT Austin. And these are some of the people that make a lot of contribution to architecture. Yeah.
It's like Turing award, right? Because Alan Turing, that's like the award for job.
Oh, he's like so think of it different. That's like the founding father, right? And then there's like the next generation.
So no call award.
Yeah, that might be. Let me look it up. Me too. Let me stop the lecture because we actually, well, let's do some trade-off real quick, right? This and this, we talk about trade-off already. This, a lot of complex instruction. If you build the microarchitecture really smartly, it can be really fast. Risk, faster clock, then you can use the transistor to implement many more things. Some of the things you're gonna learn next in the future lecture in a few, like this week, next week, and the week after. And hopefully more if you take ComArch. Some thought question that I want you to think about, right? Cost of things change all the time. Back in the day, there's a lot of companies that do sys architecture because memory is expensive. So it makes sense to do sys architecture. I want to use the transistor for non-memory stuff so that I don't have to go to memory a lot. Right? It makes sense. Now, well, memory gets cheaper. Material science, they exist and they do a lot of awesome things. So it make our life easier, make our life faster. Basically, it's like if you ask me what do I do as like a normal day living thing for ComArch people, we make computer faster. For material science people, they make computer faster and cheaper, right? Circuit people, they come up with a fancy circuit that somehow can be even faster, which I don't know why and how. But like in some cases, you don't also rarely, like you don't use this fancy instruction all the time. Like you buy your CPU, for example, how many times you use SIMD? Except for the demo in fun part. Never, right? Afterward. If you need them, you run it off some data center, not on your laptop. So does it make sense to have SIMD supported on your laptop? Yes and no. If you want to kind of like build the support for like a really fancy graphic pipeline, without relying on the GPU for some reason, I don't know why, you can maybe use SIMD, right? So it's about trade-off. So by my key message here is now you know ISA design, the rest are about trade-off. All right. I promised you about RPC demo. So the code is up on Canvas code under primitive RPC. I don't think we can cover that in 10 minutes. I already pulled off the activity on RPC because it's kind of similar to your server client interaction anyway. And don't want you to do extra work that do the same thing. The sample code is there. We use HTTP to send message over. RPC is handled as if these HTTP packets has function signature in them that say, hey, this is what you can do, X, Y, and Z. The demo only say, I want to extract the first 5 characters of the string I got. But you can imagine you can extend it to anything else. Then I have the gRPC as a demo as well, but my plan, I talked to you guys in the beginning of this class, we'll do it at the end of the semester when we are sure that we're done with ComArch module, which likely will be the last week of class. So that way you can review the material for your last quiz, and that way it will not impact what we covered on the last week because it's not going to be on your exam. All right. So I'll stop the recording now.